Hello and welcome everyone. So it's my pleasure to introduce you to Jingfeng. He's a PhD student at ME and Computing Science. And I really appreciate that at ME and Computing Science graduate students, you focus not only on what is popular and important today, but also topics that are important for the future. And continual learning is such a topic. And today, Jingfeng is going to present his work on continual learning. So it's all yours, Jingfeng.
Thank you for the introduction. So today I'll tell you about elephant neural networks. So basically in this work, we want to design a new kind of neural network that is resilient to catastrophic forgetting. So to get started, we know that in continual learning, the input data is usually non-IID, which leads to catastrophic forgetting. And by catastrophic forgetting, I mean the phenomenon that neural networks tend to forget prior knowledge drastically. And there are many algorithms that have been proposed to reduce forgetting. For example, we have replay-based methods, which basically store previous samples in a buffer and replay to their training. We have regularization-based methods, optimization-based methods, etc. And let's make a comparison between supervised learning and continual learning. So in supervised learning, we have IID samples. However, in continual learning, we have non-IID samples. We have SGD, MSProp, and add-on, and all these optimizers that are designed to optimize supervised learning tasks. And similarly, in continual learning, we have orthogonal gradient descent. We have continual backprop proposed by Sparse. We have FGD proposed by Mohammed. In terms of regularization, we can apply AO1 or AO2 regularization in supervised learning. And similarly, we have elastic weight consolidation and syntactic intelligence regularization in continual learning. And as for training strategy, we can apply dropout, early stop, learning rate decay in supervised learning. And for continual learning, we could use experience replay, pre-training, or knowledge distillation. And finally, for neural network actor, we have classical networks such as MLP and convolutional neural networks. Recently, we have GAN, ResNet, and more advanced architectures such as Transformer. But how about architecture in continual learning? We don't have something like a ResNet in supervised learning to continual learning. That is, the interaction between continual learning and neural network architectures remain to be underexplored. We don't fully understand what properties of neural networks lead to catastrophic forgetting. And are there something like ResNet in supervised learning for continual learning? As far as I know, the answer is definitely not. So we have this question: can we have neural networks that are resilient to catastrophic forgetting by design? So to answer this question, let's first investigate catastrophic forgetting from the view of training dynamics. Let's consider a regression task. Assume that at each time step t, we have a new sample arrives, and in this sample we have input x and output fx, and here fx means the true function for the input x. And we also have a neural network that is parameterized by weight w with the input x. And we have a loss function which used to minimize the error. And for example, we can use mean square error in regression task. And during training, we update weight with SGD. And here, weight is updated from W to W prime. And this delta W means the weight difference. And we can unroll it with chain rule to get two terms: the gradient of loss with respect to function, and the gradient of function with respect to W. And here, alpha means the learning rate. So now we want to know what will happen to FWX after we update the weight. So to do that, we take Taylor expansion and get this formula. So here, the left-hand side is the function change or function difference between FW prime and FW. And in the right-hand side, at least for this part, it has nothing to do with X, so we ignore it for now. And this part, which is the dot product of the two gradient vectors, in the literature, it's usually mentioned as neural tangent kernel, or NTK for short. So to continue learn, we want to achieve two goals. The first one is definitely we want to learn. That is, we want to correct the wrong prediction, which means we want the function change to be a non-zero value at point xt. This is quite reasonable, right? Otherwise, we cannot learn at all. And the second goal is to avoid forgetting. That is, when x is not xt, we don't want to change the function value. So the function change should be a zero value. So now we can see that with tail expansion, we can connect the function change with NTK here. So correspondingly, we expect this NTK to achieve two properties that are important to continual learning. The first property are called error correction. So basically, it means that when x is xt, we want this NTK to be non-zero so that we can correct the wrong prediction. The second property, we call it zero forgetting, which means for every x that is not xt, we still want to keep the value fixed. That is, this NTK is zero at point that is not xt. So by the way, if you have any question, feel free to interrupt me. Okay, let's continue. So I want to argue that it is the violation of the property T that's to the forgetting issue. But however, property is really hard to hold without sacrificing the generalization ability of deep neural networks. For example, in tabular case, we can achieve this property zero forgetting, but in tabular case, we do not have generalization ability. So in order to benefit from generalization ability of deep neural networks, we relax property 2 to get null property, which is property 3, are called local elasticity. So first, two things are relaxed. First, the equality is relaxed to be approximation. And second, we do not require x to be strictly, we relax this inequality to be a metric depend on x and xt. That is, we want x to be dissimilar enough to xt in a certain sense. And this depends on many things. For example, the data set itself and metric we consider. So what is local elasticity? To illustrate that, I'll show you a plot here. So it basically means that when we update the function value for x from this solid curve to the dotted curve, we can change the value at point x. However, we don't want x prime, the value of x prime, to be changed significantly, especially when x prime is far away from x. So basically, it means that the function change of a locally elastic neural network is constrained to be a local area around this x. Any questions for this one?
One question.
Should NT also depend on W prime? Let's check the formula. In some cases, yes. So for example, when we have deep neural networks, and this gradient vector is actually dependent on both of data and the parameterization of the neural network. Any other questions? Okay. Now let's move on. So next, I want to show you that how we can understand the success of failure of sparse representation. So generally, we believe that sparse representation are useful to reduce forgetting. And this is true, but that's not the whole story. So first, let's consider a linear function, f, which is a product between the weight and the representation of phi. And we assume phi is sparse, which means most of its elements are zeros. Also, we assume that this is not a zero vector. So the norm of this feature is greater than 0. So next, we check two properties one by one. First, for error correction, let's set x to be xt, and then we can compute the NTK in this case exactly, which is the square of the norm of this feature vector. And by assumption, it's non-zero. So we achieve zero error correction property. Next one, for local elasticity, can also compute the NTK in this case, which is the dot product of two representations. And because the representation is sparse, so in with high probability, we can see that the dot product of the two replication is close to 0. So we also achieve local elasticity. So in this case, we can conclude that sparse replication indeed can help reduce forgetting in linear approximations. Any question for this part? Okay, now let's look at the failure case. We consider an NLP with one hidden layer, and here FW is parameterized by U, V, and W. So the feature vector phi is no longer fixed. It's parameterized by V and B, and it's actually the output of a nonlinear activation function. So that's a difference from the linear case, right? And we also assume this representation to be sparse and non-zero, similar to before to the previous case. And in this case, we can do some derivation and get the NTK in this case. And compared to the previous case, besides this representation product, we have a second term which contains the gradient product. And again, we check the property one by one. So for error correction, we can see that this when x is xt, this part is non-negative. So the NTK is greater or equal to the representation product or the normal feature vector, which is non-zero. So error correction is achieved. However, for local elasticity, it no longer holds. That is because when x is not xt, this part can be close to 0. However, there's no guarantee for this part. For example, think about this mistake. Yes, think about ReLU function. When both the x and xt are positive, the gradient is always 1, so which is a constant, it's no longer close to 0. Whenever x and it holds even when x and xt are far from each other. As long as they are positive, we have this property. So so to conclude, we can see that sparse representation are not enough to reduce forgetting in nonlinear approximation cases. Any question for this part? Okay, let's move on. So besides sparse representation, what else is required to achieve local elasticity? And the answer is we also need sparse gradient. So let's look at again this NTK, and when x is not x prime, we want this NTK to be close to 0. And here the feature vector is the output of a activation function, sigma. And with sparse representation, we can guarantee that the first term is close to 0. And with sparse gradient, we can guarantee that the second term is close to 0. So together we can achieve local elasticity in nonlinear approximation cases. So together, this means that the activation function is required to generate both sparse representations and sparse gradients. So how can we obtain sparse gradient with sparse value in both at the same time? And we don't have such an activation function before. So we designed a new one, which I called elephant activation function. And it's formally defined in this formula. It has two parameters, A and D. And here's the plot for the elephant function for different parameters. So first, here the parameter A controls the width of this interval. So basically it's about 2 times A, and we can tune this parameter to control the degree of sparsity for the function value. And moreover, as you can see here, as we increase the parameter D here, the activation function, the elephant function converges to a rectangular function. And also when we increase the D, the gradient of this activation function is getting sparser and sharper. So we can see that both sparse value and the sparse gradient are achieved by this activation function.
Sorry, maybe I'm very sorry, but Is that exact 0 and exact 1 in that region, or it's the approximate 0 and 1?
Which agent?
The elephant of X, so less than -2 or greater than 2, they're kind of flat. Is that exact 0? Or
No, it's not. So when D is infinity, then it goes to we have a rectangular function. In this case, it's exact 0, but we can't have like infinity. Parameter, right? So
it's going to be approximate 0.
yes, it's going to converge to 0 slowly.
But D is fixed parameter.
In general, it's possible to tune it with all meta learning, but in our experience, we set D to be a fixed value. Let's see, there are questions. So questions is why is called an elephant? So as you can see here, the shape of this elephant is very close to the shape of our function. And that's the first reason. The second reason is that elephants are known to have a good memory, which hints the functionality of this function. That is, it helps to memorize things. Yes, and this drawing is from the book, the famous book, The Little Prince. Any other questions? Okay.
So sorry. So gradient comes at a very narrow region. So the more sparsity you have, the narrower the gradient will be.
Right, exactly. So
then how did you solve the conflicting goals? The two goals are a little bit conflicting.
Yeah, there's a trade-off between stability and plasticity. That's right. But here in this work, we focus on the forgetting issue first.
I can do a constant.
Sorry?
I can do a constant activation function.
So, sorry, what do you mean constant function?
The activation function is just 0.
Then we cannot learn, right?
It's the same thing. If your gradient is too narrow, or the non-zero gradient region is too narrow, that is similar to constant. And it's very unlikely that your new sample just hits the narrow region.
Right, no, exactly. So in that case, we lose plasticity. Okay. Next, I want to show you that with this elephant activation function, we could actually achieve local elasticity under certain conditions. And here's the theorem. Basically, when this condition holds, when D converges to infinity, and when this condition holds, then we have a 0 NTK. And the proof is actually quite intuitive. So first, when D converges to 0, then the elephant function is actually a rectangular function. So in this case, which means that for any two variables x and y that is far from each other, in this case, when they are far, the distance between these 2 points is larger than 2 times a, then there must be one point outside of this interval, which means one of the function value and the gradient value must be 0. So with this,
so D goes to infinity, you cannot learn either. Right? You will only get very large gradients if you hit the boundary.
Yeah, exactly.
And then the chance of getting that is very low. And if you don't get that, you get a 0 gradient.
Yeah, exactly. So this is just ideal case, but
it's not ideal because you cannot learn.
Yeah. I mean, in theory, we cannot learn, but in our experience, we just set D to be some small value, and so it also works. But for small d, it's really hard to prove this property.
So this is the ideal case for elasticity.
Yeah, for local elasticity.
But I can design a very simple function, which is a constant function, also has local.
I don't quite understand what you mean by constant. Maybe we can talk later. Okay. So now we have this property, then we can just use this property to prove similar results in this theory. Okay, so as Lily mentioned that, sorry, maybe not now. So next I'll introduce elephant neural network. So we call a neural network that use elephant activation functions an elephant neural network, or ENN for short. So for example, for MLP, we can have an elephant MLP. For CNN, we can have elephant CNN, and similar for ResNet. So next, we do some experiments to verify that indeed ENN can achieve local elasticity. And we use streaming learning for regression first to demonstrate that. Let's say we want to approximate sine function, which is quite simple regression task. And we have non-ID data, which means that we have stream samples, X, and Y. And here we increase X as time passes by to create this non-ID stream. And Y here is just the function value of the sine function. And we consider MLP or MLP with one hidden layer of size 1000. At each time step, the learning agent only receives one sample. So that's the typical setting for streaming learning. And next, we optimize the model with Adam optimizer by minimizing the square loss between the prediction and the true value. And we add more restrictions. So in stream learning, we can only do one single pass. That is, the agent can only observe each sample once. And we allow no buffer to store previous samples. There's no task boundary, and we do not allow pre-training either.
For every sample you see, you retrain.
Yeah, every time we see a sample, we do an update.
Okay.
Okay, so now for the methods to compare, we consider MLP with classical activation function. For example, ReLU, sigmoid, eValue, and 10H. And we also consider sparse representation methods. And to be specific, it's called sparse representation neural network, which is proposed by Vincent. And also we compare all these baselines with our methods E and MP. And here is Lily mentioned that when D goes to infinity, we cannot learn. So in this case, we set D to be a small integer, that is 8. And we'll demonstrate all the experience based on that. So first, in this table, I show you the test performance, which is measured by the mean square error for different methods. So first, you can see for all MMP methods, the test performance, the mean square error is actually very large, which means that all MLP fail in this simple regression task. Yes.
So this is non-IID data, right?
Non-ID data.
Does it depend how non-ID it is?
Yes. So the data is generated in this way. So for every time step, we have a new sample, right?
Yeah.
And here we increase X from 0 to 1. Sorry, to 2. So it's non-ID.
So this is okay. There's a very specific type of way to do it.
Yeah, there could be other ways. But for now, just consider yes.
How many data points do you have?
For the training set, I think it's about 200.
Okay.
I don't remember the test set, but it should be large.
And the error measure is in terms of the training set error.
No, it's a test error.
And
So-
the test has also been distribution. How do you decide what?
So we sample like about 500 points from the interval of 0 to 2.
But then the test set is also resampling the same thing, or you start over again?
It's a fixed test set, but we did many runs to test that, and the result is.
But there's a sequence of values. There's an order to this.
So here's what we do. For during training, we get a new sample and we do update.
In order, 1, 2, 3, up to 20, up to 500. Okay.
Yeah. No, that's 200. So
Okay.
and after update, we test the performance given the test set.
Which is numbers 501, 502, 503.
Yeah, you can say that, but still they are from the interval 0 to 2.
Still trying to understand how the sequence works out, right?
No, during test we have no sequence. We just have fixed test set.
And so those are IID?
Yeah, those are ID because we just want to compute the mean square error.
Okay, I understand what you're doing. I'm missing some of the motivation, but I understand what you're doing.
Yeah.
I want to ask, so the network still needs some generalization. Like, if this data you have 200 points, but when you have like 400 data to test, so you need, like you update X1, so you still need the data next to the X1 to resolve the error.
Yes, that's the spirit. We want to remember things, but we also want to control the generalization.
Oh.
Any other questions? Okay, let's move on. So next is the sparse representation network. So we can see that this error is slightly lower than the error of MLP, which shows that indeed we can reduce forgetting with sparse representation. However, this error is still too large, which means that it's not enough to reduce forgetting with just sparse representations. And finally is our method, which is a very low mean square error, which it shows that EMP is the only method that works well in this setting. So yes.
Yes, sorry, so how many updates did you say you made?
Sorry.
So how long is the training before you tested?
Which we have one. So for every time that we will test it.
I see.
Yeah.
So this mean square is like how many data points do you have for?
So this mean square shows the performance at the end of the training. We have like about 500 test samples.
I see. Okay.
Okay. So next, we want to see what really happened. So we plot the function values during training, and we want to show you that EMLP is really locally elastic. So first, this graph shows the sparse representation neural network at time step 100. And in this plot, the black curve shows the true function, which is sign function. And the blue curve shows you the learn function, which is represented by neural network. And the red curve shows the normalized NTK function, and normalized so that the maximum value is 1.
So to clarify, the way you learn is that the X values, they increase from 0 to 2.
Yeah.
And there are like 200 points. Each time we saw a point, like the first one was 0.02 or something, or 0.1. And then each time you saw a point, you made an update.
Yes, yes.
But then each time you looked at the performance on the whole data set, right?
Right. So
the
that's
whole
what,
data set was drawn from the true function IID, right? 500 of them. So you're trying to see like whether you remember what you learned in the past.
right, Simon?
Does it clarify?
Yeah.
Maybe you can ask more.
I'm not sure why not just assume the numbers are. I know you said it's not IID, but imagine I had the set of values of the X's. I didn't get in that particular order. I could rearrange it, and then it would be IID-ish, right? There's X and Y pairs.
But he mentioned the restriction that he's not allowed to store buffers. So if you keep a buffer, if you have a storage where you store the samples and then shuffle them and then learn, that's a pretty good way of addressing catastrophic forgetting. So he's trying to see whether he can still not forget without storing the samples. You're right. So you could store them and
Well,
shuffle them and
I meant, forget the story. You say you see the data in this order,
yes.
but what if you saw the data in a different order?
Yeah, that also works.
Yeah, so it works. Why not just view it as IID data? There have
So-
the X, Y pairs, and you told me how to function, and then X drawn uniformly from, your
Because if it's streaming learning setting, you don't have a choice on the sequence of the data. Data comes in a sequence that is provided by the work. So he's assuming that data is coming in this particular non-IID stream.
You make like a real world example is if, let's say you already have a learned model. And then you, all of a sudden you have new data that like is available and you want to train on that data. And then after a while, maybe let's say you're able to change new data and now you want to train on that.
I understand.
Yeah.
But I mean, you did the same experiment you did right now, but instead of seeing the data in this order, you saw it in a different order.
Then all this method will work because there's
And we know that it's gonna work.
Yeah.
The whole point is that in the real world, we cannot just shuffle the feature sequence. The feature sequence is determined by the work, right?
I understand.
And we don't have a choice. We have to
But
see
the
that.
data you're testing on is interspliced with those values, right?
That's true. That's true. We are trying to see whether we can remember the whole function while we are learning non-IID, which is difficult, right? So because you might be always learning about the current sample and forgetting the past one.
Yeah. Okay, I'll keep thinking about it.
thank you for discussion anyway. So okay, let's continue. So next is the dotted yellow orange line, which shows the sample we have. So for time step 100, we have xt equals 1 here. And as you can see that the blue curve and the black curve intersect at this point, which means that indeed they can learn a good value, a good approximation for this data sample. However, it forgets all previous samples. This is what we want to show. We want to show that is in non-IID setting, we have catastrophic forgetting, even for this simple regression task. And similarly, as we move on, at time step 150, the blue curve and the black curve also intersect at point xt. However, the previous approximation, they are all lost during training. And in the end, we get something like this. So basically, as you can see here, although we have a nonlinear approximation function, this blue curve evolves like a linear approximation, which means that it forgets previous learned knowledge. And now let's take a look at the EMLP. And again, we have blue curve, black curve, and the normalized NTK. And we can see here, the blue curve intersects with the black curve at point xt, which means we can achieve a good approximation. And more importantly, that all these previous approximations are well kept. So there's less forgetting compared to SRN case. And finally, the NTK function also demonstrates that, for example, at point xt, the NTK function is non-zero. And when x moves away from this NTK, the NTK function soon converges to 0. That's what we want for local elasticity. When x is far away from xt, we want this NTK function to be close to 0. And this is a demonstration. And as training moves on, we can observe a similar phenomenon that this EMMP is able to remember previous prediction. Again, the NTK is in a good shape. And in the end, we achieve a good approximation of the sign function. Yes.
I have a question. Like, since it's a neural network, each time you learn, you only have a small learning rate. So when you draw this picture, like at each point, you just learn one time, or learn many times until the error get close to the real.
Yeah, we can learn many times. We can also use a large enough learning rate so that we can achieve a good approximation. Both are okay in this case. Any other questions? Okay, so next, I'll show you something more that is with local elasticity, we can update the run prediction by editing the outputs of a neural network near pointwise, and this is quite useful. So first, we have step 1, which I call pre-training. We first train a model to approximate the sign function in the traditional supervised learning style. That is, the input data is ID. And next, we do fine-tuning. We want to update the prediction of the model for some specific input X from Y to Y prime. And this is quite common, especially in reinforcement learning, because in reinforcement learning, we have TD learning, and the target of TD learning is changing during learning, and which requires us to update the Q value function or the state value function towards the new target in the whole process of training. I see there's a question. So how did NLP evolve on this sign task? So this is plot in these 3 graphs. And basically this EMP evolves as a linear model. And in the end, we get a really bad approximation.
No, this is not EMP.
Oh, all right. So sorry. So the
next three figures.
Sorry?
The next 3 figures.
That I think he asked MLP, right? Yeah, he asked MLP.
Oh,
So
okay.
the behavior of MLP is very close to SR in this case. So I didn't show here, but basically it also evolves as a linear model. So we have this setting, and to be specific, we choose X to be 1.5, choose Y is -1, and the new target is minus 1.5. So now let's take a look what really happened during this fine-tuning step. Here the black curve shows the old learn function, which is a learn function after step 1. And this new learn function is plotted in blue curve. And we want to update the old prediction towards the new prediction. So as you can see, we indeed can successfully correct the prediction from the old one to the new one. However, the function values for other parts, for other input domain, is also significantly changed. That's not what we want, because it causes forgetting. And for ENLP, there's no such issue. We can still correct the old prediction towards the new prediction. And more importantly, the function values for other parts remain basically the same. And the change of function is constrained to be a local area around this point 1.5. No question? No question. So, yes.
Is this increasing the variance of the model? Sure, learning compared to like a similarly sized MLP, would that increase the variance of it?
What do you mean the variance of prediction? I didn't consider that, because in this task, the main goal is to show that we can correct the function value, but not the variance. I'm not sure about that. Any other questions? Great. So this is quite useful in reinforcement learning, and I also have experience to demonstrate that.
Questions?
Yes.
So I get the motivation. I understand the 20 examples here. Motivation was I trained a model to work in summertime in Edmonton, and I got tools that work really well in that context. And now the seasons are changing, and it becomes colder and colder. And now certainly I want to, I decide local decisions, but I throw a warmer jacket, but also my car won't start, right? So there are some non-local things that happen. Could you give like a motivating example of why you want this behavior where it only changed very locally, and you can sort of give me the motivation for why this makes sense?
Oh, well, I think the best example would be large language model, where we have new data coming and we want to fine tuning it. However, we don't want to forget the previous learned knowledge, right?
Well,
We only want to update.
well, what if the new knowledge makes all I learned a lot about Newtonian physics, and I got that work, and all of a sudden I now know there's Einsteinian models, and the Newtonian isn't completely wrong, but everything changes a bit, doesn't it? Because like the path is completely right.
Well, that's a quite different scenario, I guess.
Is it?
So basically, we want to change. We still want generalization, as you mentioned. When the physical law change, we want to change something that's quite similar for the similar cases.
Or maybe not. Maybe it should be very different.
That's basically defined by how you define so that's basically based on how you define the difference, right?
Yeah.
So that's another.
That's why I was asking for motivation. You're saying about it. I'm still trying to get a clear example where I can say I want to change just exactly this and nothing else changes. Like imagine some changes have manifestations that mean everything else I learned had been modified a little bit.
Okay, then let's take our example. Let's say this is a state value function, and
or maybe your example that you gave. I like that. Summer, right? Summertime, I learned how to live in Edmonton, and then winter time, I learned something new. So what happens to the existing models is that it also changes my summer way of living life, right? So in winter, I learned that I have to wear heavy coats. Then in my internal model, I think that okay, in summer I will also have to wear some heavy coats, or at least light coats. Whereas the motivation is that shouldn't happen in summer. Like my decision that I learned in summer, that should stay.
I switch up a context. In summertime, I do this. In wintertime, so I learned that I have to just wear short pants and t-shirts all year, all the time. And that's my model of the world.
Yeah.
And then later on, I realized, oh, that doesn't work. It's for me and in wintertime. So now I have to learn a whole different thing. That says I have to listen to the news report in the morning, so the weather's going to be, which I didn't do most of the time, but that changed my whole model.
Instead of changing the whole model, I change model only for the region. Like whatever I learned in summer.
Learn that I have to know it's going to win from some. Which I didn't know
Yeah.
before. Is that pretty much change?
Well, if your representation is sparse and then also the gradients are sparse, you will not change things for summer. That's what he's good for.
Okay, right, okay.
That's how we keep sparse representation, right? For us, summer and winter, they are separate things.
Well, once I know to look at the weather report, then
That's right.
I didn't know to look at that.
I have a question. So, since you have like your method with your elephant activation function, your gradients is very sparse. You're just editing like or changing the function very limitedly. But like I'm looking at these two like diagrams. I'm like wondering which one is better. Because do you have analysis on like when you use elephant activation, how does it affect like generalization? Because for example, you're looking at data streams that have like can potentially have a distribution shift. And then looking at these diagrams, it's unclear which one is better because on the right hand side, it seems like you're only memorizing the new data sample, whereas on the left hand side, you somehow can like actually learn maybe the whole distribution has been shifted down. So like it's hard to tell whether this is helpful in generalization. Kind of.
Yeah, that's a good question. So here the question is, how much generalization do we need actually? So with traditional, for example, MLP, we cannot really control it, but with the elephant neural network, we can control it by changing the for example, the weight of the elephant function or the parameter D. So we basically want to break the generalization ability of neural network so that we can control it in a small local area. But how small of this local area is totally controlled by some parameters. I think we have some online questions. So I'll read it. So
Maybe you can continue.
Yeah.
And come back to Jacob.
okay, thank you. So to summarize, we showed that sparse representation are useful but are not effective enough to solve streaming regression tasks. And the EMMP is locally elastic when D is small, and it allows to add the outputs of function value nearly pointwisely. And finally, EMLP can continually learn to solve regression tasks by reducing forgetting. Next, I'll show you some examples in classification tasks. To be more specific, we consider class incremental learning, where samples from new classes arrive incrementally. And we add the following constraints to make it more difficult. So again, we have one-time pass. Each sample only occurs once during training, and the task boundary are not provided or inferred. And we do not allow pre-training or a fixed feature encoder. And finally, we do not have a buffer to store previous samples. And first, I will compare these methods. First is the traditional MLP and CNN with value activation function. And also consider a variant of EWC that is designed for streaming learning. And we consider two sparse representation methods, SD, MLP, and the fly model. These two models are bio-inspired. I'll not give more details for now. And finally, is our method. We consider EMLP and ECN with D equals 4. So this shows the result on small data set called split and list. And it's quite big table, so I'll walk you through step by step. So first, the neural here means the size of the hidden layer, and we consider two sizes, 1,000 and 10,000. And data set capacity means how many times the model can observe the same data. So for example, for SDMLP, it observes the same data 500 times. And next, the task boundary means whether the method is utilizing the task boundary information or not. And here only the fly model uses this information. And as you can see here in this strict setting, when there's no task boundary, one single data path, the best model is the ECN model, which achieves a task accuracy about 85%. So ECN is the best method in this setting. And next, when we increase the number of neurons from 1,000 to 10,000, we can see that the performance is generally increased. So this result indicates that why the neural networks forget less, because they have more neurons. Next, we compare different structures. The first one is basically MLP structure, and the second one is CNN structure. And we see that there's a very large gap between these two structures. So this result shows that neural network architectures can significantly impact learning performance as well in this setting. And finally, here we have three methods: CNN plus streaming EWC, and our method ECN. And you can see that as when streaming EWC is added, the performance is also increased slightly by about 1%. However, if you use another structure, ECN, to be specific, we have a very large improvement. So this means that the architectural improvement could be larger than algorithmic improvement as well. And we also test the, question.
Sorry, can you say more about the task? So you start with fixed labels and then do the labels change over time, or so you just go through the entire data set?
Yeah, I should skip that. So basically, in MNIST, we have 10 digits, like from 0 to 9. And for split MNIST, we have we split into different classes given the task, given the label. So for example, at the beginning of the training, we have only samples that are zeros, and then we have samples that are labeled 1 and 2. So
Thanks.
Thank you.
And the test set has all 10 digits.
Yeah.
So initially I'm going to be crap because I've only seen zeros at first.
Yes.
Then eventually,
Right. Okay, so we also test in CIFAR 10, and basically you can see that the performance of ECN is also the best. It achieves a 25% accuracy. However, compared with MNIST, its performance is quite low, which means that it's still hard to get a good performance in split CIFAR 10 in our setting, because CIFAR 10 is generally a much harder task than MNIST in this case. So
and here again, you see pictures of horses first, and then you see pictures of dogs.
Yeah, exactly.
And there's no mixture.
There's no mixture.
Okay.
So next because this setting is so hard, we add pre-training back, and we use a fixed feature encoder to encode this CIFAR 10 image to feature of two image embeddings, and the dimension of this figure is reduced so that we can get a better representations. And as you can see here, the performance of our method is significantly increased from 25% to 75%, which shows that pre-training is really helpful. And the reason is that by using pre-training, we can get a better representations. And finally, we also test our method in reinforced learning. And first, I will show you why we should use reinforced learning as a benchmark. This is basically because we still have like catastrophic forgetting even in single IO task. And I'll show you example. So here we consider two variants of DQN. The first one, the red DQN, is a DQN with a large buffer. And in this case, it's set to be 10,000. The orange one is called DQN-S, which has a small buffer, about the size of 32 in this case. And we can test it on mountain car and plot the learning curve. And basically, you can see that the performance gap between these two agents is really large. And to see why this is happening, we plot the greedy action during training for these two DQN variants. And here, the greedy action means the argmax of the Q value for some specific state S. And as you can, so for this state, the optimal action is 1. So as you can see, for DQN with a large buffer, the greedy action oscillates at the beginning of training, but soon they converge to the optimal action. and we have a very good performance. However, for DQNS, the grid action oscillates during the whole process of training. So it's quite unstable, so it reduces performance. And with this experiment, you can see that the forgetting issue exists even in single IO tasks, and it's largely masked by using a large replay buffer. And when the replay buffer is small, solving an IO task requires continual learning ability for both classification and the regression. And for example, by selecting the optimal action, we're actually doing something similar to continual classification. Assume that we have a discrete action spaces. And for TD learning, we have it's actually required to the model to do continual regression because during training, this target is changing, similar to what we show in the editing a sign function experiment. So next, we do some experiments to verify that we can see 4 tasks: London car, everybody, culture, and pigs copter. We use DQ is the baseline algorithm. And the model we consider are MLP or EMLP with one hidden layer of size 1000, and D is set to be 4 in this case for the elephant function. And next, the buffer size we consider have 2 options. One is small, one is large. And here are the learning curves of different methods. So for MLP, we consider 2 buffer sizes, 10,000 and 32. And you can see, again, that the performance gap is quite large. And this is true also for other 3 environments. And for our method, EMLP, which has a small buffer 32, it basically achieves similar performance or slightly worse compared to MLP with a large buffer. Except pixel copter, but still in pixel copter, our method EMLP is still significantly better than the MLP with a small buffer. So basically, we can conclude that in IO tasks, EMLP is more resilient to catastrophic forgetting than MLP. Any other questions? Okay, so finally, to conclude, we start the role of activation functions in training dimensional neural networks and their impact on catastrophic forgetting. We found that besides Sparse representations, the gradient sparsity of the activation functions also plays a very important role in reduced forgetting. And we propose a new activation function called elephant activation functions that can generate both sparse representation and sparse gradients. And finally, we significantly improve the resilience of neural networks to forgetting by simply using the new activation functions. And our method is widely applicable in different scenarios, including continual classification, continual regression, and the reinforced learning tasks. Yeah, that's all I have.
Thanks for that. So in traditional neural networks, activation functions are rooted. The activation functions are monotonic. So basically it says, if you have a larger feature and some kind of abstract feature is more satisfied and it has a higher value. But in your case, your activation is not monotonic.
I think that's fine. For example, for liquid value,
it's still monotonic. Liquid value is still monotonic.
Oh, you mean
monotonic just means your input feature is larger. After some linear combination, if the feature is larger, you have some abstract feature, it's more satisfied and have a larger value. But in your case, it's not monotonic. Let's say how good it is. If you have very small region, you say bad. And then in the middle, you say, oh, it's really good. But then if it's even better, now you say it's better again. So do you have any comment on its role in the neural network setting?
I'm not sure exactly, but I still think that we have something, we could still have universal approximate theory, even for non-monotonic activation function, but I'm not sure.
Okay, how is your activation performing in the IID case? Just like supervised learning and train a, let's say, image net. It's not a toy task. Let's try some image net. I just train it as usual. Does it work well? Or
I didn't test that for in that complex data set, but at least for this simple task plus sign function.
This is.
Yeah, this is a bit trivial, but I didn't test that because I focus on like non-ID learning setting. But yeah, it's interesting to see how it performs in supervised learning. That's right. Yes.
And the classification experiment, how many hidden layers will be there?
How many what?
How many hidden layers?
Oh, just one has one hidden layer for MLP. And for CNN, we have one convolutional network connected with one MLP.
We tried with all the hidden layers.
Yeah. We have tried that, and the problem is that the performance decreases mentioned by Lily because we suffer from catastrophic, loss of plasticity, and so there's a balance between stability and plasticity. That's one future direction.
So I really like the idea. I think the main contribution sort of is that by controlling DNA, you can control the extent to which you want the network to generalize.
Yeah,
It's
we
a
are.
good thing, and maybe eventually you'll have some meta learning way to learn that for each neuron individually. Maybe. But have you tested like how much DNA affect the performance in these cases? Like if you vary DNA, like how is the performance sensitive to those parameters?
It actually depends on data set. So, for example, when the local elasticity, when we want to see how X is different from another X prime, that's totally dependent on data set. So in order to perform well, we indeed need to tune in the hyperparameter to get a good performance. And whether it's sensitive or not, it totally depends on data set itself.
But like how sensitive? Is it like exactly one value where it works, or is it like reasonably wide range?
I would say it's a reasonably wide range.
Can you recommend like one value that will work well?
So
like all tasks?
for the split MNIST, it's about 0.5 for the parameter A, and for D, we can set to 2 or 4. Yes.
What are the variants of A in all these experiments you did mention?
Oh, right.
Is it or
I tune it actually, so it's selected from a small range. Yes.
So it's been shown that like in past works where with flatter activation functions typically suffer from vanishing gradients and learn much slower than something like, for example, ReLU. So like in your experience, like did you experience that your elephant activation function learns like less efficiently than something like ReLU?
You mean you supervised learning setting?
Sure. Yeah.
I don't test extensively supervised learning as I answered to Lily.
Yeah.
But at least in continual learning, sometimes we don't want to learn faster because the more you updates, the more you forget.
Yeah.
So it's something that we do need to control about. Questions? Abhishek, do you have questions?
I have a quick one, which is so this is very interesting, right? So this ensures that the learn function doesn't forget what happens in the previous outputs. I was wondering how robust this would be to like noise, right? Because it must capture onto the noise, but yeah, we can talk about that later. The more interesting question to me is like, so for example, you motivated this by saying that there was some discussion about like summer, winter and stuff. And so for example, now winter is coming and now some of us will be going back to our, snowboarding, skating sort of activities. And you would like, ideally, we would just start off where we left off, right? Like, let's say I had achieved some ability last winter in snowboarding, and then I would assume that I have not done it for 6 months now, but the day that I start, I will start at the ability that I left in, let's say, March, right? That would be ideal, but that's not what happens, right? Like usually we take a few days to get back to that thing, to that level, and then maybe improve further. So I think of that as, maybe I I sort of forget that function in terms of in favor of things that I need right away, like in the summer, but I sort of keep the representations or something like that around, right? And so that once I'm exposed to that task again, I can use those representation to quickly learn again. But it's not that I'm not forgetting the function itself. I think I am forgetting the function. It's just that I sort of have the representations intact. And so I don't know. Yeah. So this is sort of philosophical. So I was just wondering, what are your thoughts about that? Do you think we should or want to not forget the function at all, or is it something lower level than that?
Okay, so as far as I understand, basically it's a problem connect to both catastrophic forgetting and plasticity, right? You are mentioned that when we forget, we don't forget it completely. We can still quickly learn when we have when we are required to perform the previous task, for example, snowboarding, something like that. Then I think that's because we are human beings. We have kind of memory and we don't casually forget totally. But for neural networks, what you can see in a simple regression task, even for approximating the sine function, it totally forgets.
Yeah, so I agree that this method is doing something more. I'm just wondering in general that we as humans or other animals, do we tend to maybe not catastrophically, but just forget some of the function itself, or do we forget the entire representation? Like, yeah, this is a very philosophical at this point, so it's okay. We can discuss it later.
Okay, thank you for the question. David, can you see your question?
Hi, yeah, I wrote it down. Should I say it? Yeah, so my question was if there's other activation functions that have similar properties. I guess maybe I don't necessarily remember all the properties required, but for example, a very sharp sigmoid function, would that have the same desired properties?
Right, well, we discussed many options about sigmoid function, about activation function, and I have a result in the paper, but not in the slide. So basically, all other known activation functions, they could not generate sparse representations and sparse gradient at the same time.
If it was sharp sigmoid function, like it wouldn't satisfy condition 1, right?
Yeah, because the representation, for example, for at least half the function value is non-zero, right, for sigmoid. Although the gradient could be sparse.
How about shift sigmoid?
What is the shift?
Just shift the sigmoid to, let's say, a large number. The standard right now, the standard is 0, but now I set it at 10.
You mean the
sigmoid? I just shifted it to 10. So any feature that is greater than 10, I feel is unlikely. Then most of them will be 0. Only if you get a feature that is greater than 10 will be non-zero, and a feature, your gradient only applies to whose feature is greater than 10. So I just move the sigmoid to, let's say, standard at 10 or standard at 20. Then it will satisfy both properties.
I don't think so. In that case, when x is larger than 10, you still have
it's unlikely. If you try to check, let's say 10,000 samples, only maybe 20 of those samples will be
I see.
Okay.
Then that's possible. If we constrain the input domain. Right.
Yeah.
Any other questions?
By the way, how important is the monotonic property of the activation function?
What do you think?
I don't know. I feel it's very important because the original idea of feature is like how satisfied it is. For example, if you do CNN, it says, oh, this filter says whether you have a pattern of, let's say, strips or alternating strips with certain frequency. And if your answer is yes, then it gives you a large feature. If your answer is no, then you give a low feature. And it can synthesize the abstraction of different features among layers through the deep layers, and it gives you a very powerful model. But if your activation function is non-monotonic, it's unfamiliar to me. I don't know what happens.
I remember I read this paper where they tried, just absolute value of X as the activation function. It didn't work really well.
Okay, absolute value of X.
Interesting. I think non-linearity is the most important thing. I'm not sure about the monotonicity. Yes.
So I have a question in your last
Last.
RL experiment.
Which experiment? IO experiment?
Yeah, the RL experiment, the last.
Yes.
So your conclusion is that like we have like improvement in performance because ENNs like mitigate catastrophic forgetting, right? But can I look at these results and say the same thing, but like replace catastrophic forgetting with also plasticity?
Well, we have yeah, that's true. So this could be, but so as you notice here, I use very wide network. It's 1,000. So potentially, I hope we can reduce the loss of plasticity issue in this with this set.
But so at the beginning, you use the notion of NTK and for AN and NTK would be very small when X and X and like when two inputs are dissimilar. Right, but you don't use that here to show that in fact, like we have the issue of catastrophic forgetting with the smaller with MLP with smaller block, right?
I think I showed. Are you talking about this slide?
So I'm not sure if this shows that we have to forget.
So here, as you can see, so that's considered like classification task. Basically, we want to select the optimal action line. And here in this plot, we can see that the greedy action of DQ with the large bound converge to the optimal action. However, for the greedy action of the small with DQ with the smaller buffer, it oscillates. So it learns and forgets and relearn and forgets.
So I understand that like we have oscillation with smaller buffer, but like I don't see the connection that this is forget.
It forgets previous, for example, it learns the greedy action is the optimal action and then it forgets. And that's the forgetting I'm talking about. Or maybe you have different idea about forgetting.
So I was hoping that like you define forgetting at the beginning, but here you're using some other proxy for forgetting. So
Yes,
like
yes.
I agree with that first one, but I don't agree with like forgetting in this slide because we can have so many things happening in RL and people can like see performance drop and see that and say that this is loss of plasticity. Other people can say this is catastrophic forgetting.
But this is not just a performance drop though. The other figure is also showing the output of the critic. That's not performance, that's what it learned. Right? It learned to, at the beginning, it learned to have the highest value for the optimal action. So if you don't have that anymore later, what would you call that? You learned something and then you don't have that anymore. You learn the right thing and then you don't have that anymore. What do you want to call that?
Sure, but why I cannot like it seems like okay, I forgot, but maybe I can relearn it again. But
Okay, so that's good. You already admitted that you forgot, right?
Sure.
So
yes.
he's not claiming that we don't have other things. He's claiming that that's at least showing that there is forgetting.
Okay, I agree that at least we have forgetting, but we might have other things too.
Absolutely.
And it's not clear that in this experiment, ENNs improves performance because it mitigates the forget. Maybe someone can say because it activates at very like when X is small, maybe it enforces like weights to be smaller, and in that case, maybe it would improve plasticity. It's not clear. That's what I'm saying.
Yeah, good question. So I think for when I talk forget here, I'm saying that it's kind of a phenomenon. For example, forget previously learned optimal action, and there could be many causes, as you mentioned. But still, what I want to show here is that we can indeed reduce this phenomenon.
I think it'd be more convincing if you also have a plot like this for the EDQN.
Yeah, right. I should probably do that. Thank you. Yes.
So would you go back to this slide where you change it for minus 1.5 there?
This slide.
So what is happening there? It's like you are the update is very related to the X value that you are searching right now. So aren't you like getting a high variance because we're only changing exactly for the point X? So your bias will be very slow. And then wouldn't that make it harder for generalization?
So when you see variance, what kind of variance I'm talking about?
So like your update in this case, it's for X equal 1.5. And then you're just saying, oh, the update is going to be related only for that type of X. So when you're doing updates related to your inputs, and they are very specific and they gradient only changes in that region, isn't that making it harder for generalization for if your inputs a little bit different? So how does that work? Like how do you manage to generalize?
So in this version, basically, I want to say that the traditional MLP is kind of over generalized. So we want to break this generalization. I want to control the generalization to a local area. That's the spirit. And that's what we want. So once we can control that, we may reduce forgetting.
Okay.
Any other questions? Okay, thank you for joining, and it's very a good experience talking to you guys.